I did put the slides on the thing in case you want to. Okay, let's get started. Today it's a somewhat of a mixed topic class. You read Lin Guan's paper on combining PDL and RL, but that sort of presupposes that you know what RL is. And we had this conversation, some of you know, some of you don't. I told you there's a RL stuff in Intro to AI that you should follow up. But I don't know how many of you did. So what I'm going to do today, essentially, actually, normally RL is its own course. Everything in this class is its own course. Many classes, that's the way it is. But, and certainly even in the Intro to AI, I wind up teaching like multiple classes on RL. And you can redo that again in graduate level class because nobody pays any attention anyway. But what I'm going to do is kind of condense. This is my ambitious way. I guess you kind of realize that there is like a significant shrinkage from the pre-class slides to post-class slides. They're like, I put like 175 just in case I run out of things to talk about, and then I go back and I find that I completed about 20 slides, and so I just only put that. So basically I have like three-part thing. I'm going to just do very quick introduction to MDPs and RL. It's going to be probably not enough if you don't know anything about MDPs and RL, so this is just to kind of get you some of the terminology right, but it's not at all enough. You have to actually, the minimum you have to do is, as I said, do those lectures that I mentioned. But I have to say that because to actually make any connections to what's happening in ASGRL paper, which will be in the end of the thing. Plus also later on we'll talk about like LLM, RL connection, all of these. Basically you need to know what RL is, right? At some level. And then I also will spend some time talking about planning and RL connection. So it turns out that, for RL is a more general idea, but there is a little part where essentially planning and RL are trying to solve the exact same problem. Okay, so I actually have, I think somebody has tweeted, maybe Oscar Wilde has tweeted that America and Great Britain are two great countries separated by a common language. So in the sense, the same language, but they speak differently. And so it turns out that planning and RL are two great areas separated by a common terminology, which they basically are a common problem, but they don't talk to each other as much in terms of the people who tend to do this tend to be in different places. So I want to actually make some connections that are very useful to understand what's going on, with respect to this class. You can then arbitrage that. And then finally, I will get to ASGRL paper, that Lin Guan's paper, almost as sort of a way of connecting some of these connections I made between planning and RL. Plus, as you probably found from reading it, that it connects like a whole bunch of things. It has the notion of abstraction because symbolic models are the abstract part and the RL options are the more concrete part. And it also combines like more PDDL style planning with RL style options, etc. I'm not saying that it is like the best thing in the world. It's just one way of putting the different pieces, and so that might give you ideas. So that's what I'm going to do. And you also read that, so you can, while we are going through the rest of the class, you might have some connections that arise in your own minds. Okay, so that's what I am planning to do today. And like I said, the stuff on the quick introduction to RL and MDP might be too sort of obvious to people who know a lot about MDPs and RL, and probably not anywhere near enough for people who never heard of MDPs and RL. but I had to do something just so that we at least pretend to be on a common ground, essentially. Okay, so that's what I'm going to do. So one thing I want to do before just going in like more of a small digression is, remember last class we talked about one type of abstraction was the precondition abstraction or a detail abstraction. And I don't know how many of you remember, maybe let me repeat this thing that, so one idea would be that if you're doing, let's say, PDL planning with STRIPS type of algorithm, STRIPS type mean sense analysis algorithm, let's say, you might essentially say that the preconditions of the actions are given numbers, level 1, level 2, level 3. 1 being, let's say, the most important, 2 being second most important, 3 being the third most important. So they are like, the preconditions are stratified. You see what I'm saying? So for example, to go to San Francisco, I need to have a flight ticket, I need to have an Uber, I need to have my shoes on. And one might think that flight ticket is probably the most important thing. Putting shoes on and having Uber is like much simpler thing, because you can always do that in the last minute. So you could actually give lower level numbers to that. And the idea then is you make the plan work for all the higher level preconditions, and then work for the next level preconditions and the next level preconditions. This would have made a lot of sense. Of course, it was like a big deal, as I mentioned last class. At the time of strips, there is this idea called, right after that, there was an idea called abstrips. Abstrips is a abstraction-oriented strips algorithm. And all they did was essentially assuming that these numbers are given. Like, just like I said for this flight thing, I kind of said it's reasonable to give having ticket to be more important precondition than putting on the shoe, having shoes on. And you all agreed, and so we kind of decided to put that. So again, along with giving the domain, we also give the importance of the conditions in the domain. Right? That's what one of the things that we were doing in the hierarchical task networks too, because we are assuming that the domain writer can give those things, right? Of course, in the case of strips, of course, it becomes actually interesting after you do this. Even if people gave you these numbers, it becomes actually a sort of an interesting problem to first to come up with plans in the levels of abstraction. Okay, because in the case of strips, what happens basically is if you're only considering, let's say, the high level actions, then remember strips basically gives you plans where the actions are next to each other, they're contiguous. There is no precedence relation in strips. Right? So you might actually have a plan that sort of, so actually let me just make it slightly, if you look at that close, that will look kind of bad. So let's just say contiguity relation is some sort of a concrete, connection between the actions. So there's an action, there's an action, there's an action, and there's like some kind of a cement thing connecting them. So nothing else can come in between. Right? That's like a high level plan for the first level conditions. Now you want to work on the second level conditions. So the second level conditions, what you will wind up doing is, let's say, again, of course, you can also have initial state, and then initial state has something like this. So from basically in this plan, then from here, you will consider second level preconditions, and then try to do a strips plan for this work. And then similarly, you can consider second, and having done this, you'll now have a complete state here. You'll take the second level preconditions here as the new goals and try to do a plan here. Do you understand what I'm saying? So this is like, to make sure that you do it right, it's like a slightly more technically complicated thing, first of all. And I also mentioned that instead of strips, if you did, let's say, ABSNLP. SNLP is the name of one of the partial order planners, in case I may have mentioned this, So if you do ABSNLP, then essentially it just becomes a open condition ordering. So you work on the first level open conditions, after that the second level, after the third level, and there is nothing different. It's just, open conditions can be handled in any order you want. If you believe abstraction helps, you work in that order. Do you see what I'm saying? So this was one of the things that it became only slowly obvious to the community Back in 72, there were abstracts, and then there was people interested in trying to say, how do you then get these numbers for the preconditions? Right? Because I'm just telling you that I'll give you the numbers. And in fact, in Block's world, it's not even obvious what are more important and what are less important conditions for the, for the actions. But that, be that as it may, there was this guy called Craig Knobloch who essentially came up with a particular idea for kind of connect, like an operator graph. The details are not kind of you'll see why I'm saying this whole thing in a minute. But so he basically had come up with an idea of coming up with some numbers for the preconditions by essentially having some notion of this thing called operator graphs, which is some sort of a dependency between the actions in the PDL part. And then he basically showed that that seems to work in abstracts. And this was in 1991, 1990, AAA, and he had like 3 papers on related ideas in AAA. AAA at that time was NeurIPS, ICML, and IEEE combined, because there was no other conference like that. Each guy in AAA was rolling on. So there are 3 papers from this one guy. And so we used to make jokes that there's Block's world and there's Knobloch's world, because Knobloch is the guy, and because he has 3 papers. And then turned out that what I was telling you, which is basically if you actually think of it in terms of like a real abstraction should depend on the way the planning algorithm is written. Do you guys understand that? So if you think that this is more important, this is less important condition, etc., that should be independent of whether you're doing strips planning or plan space planning or some other planning. You would think that, right? That's a reasonable thing. So by about 1992, which is like, I guess, 2 years or 2 years or later, there's this guy called David Smith basically wrote a short paper in planning conference called AIPS, which actually happens to be the very first automated planning conference, in the sense that there used to be AAAI, there was a general conference, and then there was like a conference for just planning. And it started, there were like 2 different ones. One's called EWSP, European Workshop on Planning, and the other one is this planning conference. And the first one was held in Maryland. And actually, so that was 1992. And anyway, there was like a short paper by this guy called David Smith that basically showed if you really do this in the context of plan space planning, because by that time people actually are a lot more into plan space planning rather than strips planning, there's not really any difference. And in fact, what matters, what we're saying in that case is what matters really is not this some static distinction, static stratification of conditions based on the operator graph, but how easy or hard is it to make a condition true in terms of like the shorter plans versus very few long plans that are available for making a condition. That's a different notion of abstraction. And then he basically gave some counterexamples saying Knobloch's thing actually doesn't work in plan space planning. I showed this slide last week, and I went through it very fast. The reason I'm saying this here is this was day before yesterday, that's Craig Knobloch. So there are actually people behind ideas. Where is this slide? I forget. Let's see. Yeah, that's good. So he was visiting his mom in Tucson, and so he came up from Tucson for 1 hour. I went down from Tempe for 1 hour, and we met in Eloy. It turns out if you ever need to find out what's the central point between Tucson and Tempe, it's Eloy, where nothing else exists other than this one restaurant called Paloma, La Paloma, and we had a nice dinner, a nice lunch, and this. Now, this is David Smith, the guy who actually wrote the other paper showing that Craig Knobloch's idea actually doesn't make sense from abstraction. And part of the point I'm trying to make is, honestly, interestingly, research itself is a community to some extent. If you hang around, in any community, you will have, like, if you hang around in some McDonald's, you will make friends in McDonald's, right? And if you hang around in research McDonald's, which is what we do, we have friends, lifelong friends almost. So essentially, so this guy, David Smith, he has come multiple times. We have actually papers together too. And this was at his home. He has like a lovely home in Los Altos. He worked for a long time in NASA. And then since I'm showing pictures for whatever the heck reason, that is damn bad. This was like also like just before the end of our spring break. He spent like 1 week in Sedona, coming from Seattle, in South Square. So anyway, so there are all these people who are there behind, other than the guy who's also talking to you. Okay. But the bigger point, of course, is remember that I repeated the precondition abstraction and why it may be kind of harder if you just give numbers. It may be harder to handle it for strips kind of a planner because you need to essentially put new guys in this cemented area, right? Because you have to put new actions in the cemented area. But if it is plan space planning, everything is basically precedence relation. So things can come between existing guys. It's not even a deal. Okay? And then keep that in mind. Anyway, so actually, in fact, let me say one more thing which is actually useful. That sort of gives you connections as to how people come up with ideas. So David Smith's original PhD dissertation work, that was way before 1992, was something that makes sense to you too, which is how many of you heard of things like Prolog? Okay, so some of you heard Prolog, right? So Prolog, you will say, you can write things like this. If you want to prove something to be pet X, then you would say, apartment pet X. Okay, then it needs to be a pet, and it needs to be small. Because it's kind of hard to have elephants in the apartment. An apartment pet is basically a pet that you can have in your apartment, right? So I wrote up this little thing, like apartment pet X is pet X and small x. Now, if you remember anything at all by mistake about Prolog, you might remember that the way it works is to prove that something is an apartment pet, it tries to prove that it is both a pet and it's small. The question is, which order should it try to prove? Or at least, in fact, instead of proving, in fact, it actually is looking for apartment pets. So it wants to generate large number of values for x that satisfy small x and pet x. So the question is, among these two, so you need to basically find something that is a pet and then see if it is small, or find something that is small and see if it is pet. Right? And if you don't do it, like for example, it turns out that you're talking about the universe of objects, okay? And if I first try to see something that is small and then check if it is a pet, it'll be a wasted effort. Do you understand what I'm saying? There are like way too many things that are small, and most of them are not pets. So in that sense, actually, the right order is essentially to check if it is a pet and see if it happens to be small. On the other hand, if you're running this in a pet store, that is your database essentially is not the universe of objects, but the universe of things in a pet store. Then actually everything is a pet there. Because that's why it's a pet store. Other than the owner, okay? Everything is a pet, right? But only few of them are probably small and some are probably big, etc. Right? Instead of pet store, you can also do zoo. It will work just as well. So suddenly the order changes. You would actually try to look for something that is small and then show that it is a pet, rather than look for something that is a pet and show that it's small. So to some extent, this actually points out that abstraction is also dependent on the sort of objects that you have, the universe in which you are operating. And so he basically brings this idea, he had like a PhD work on this, and he basically found some ways of actually computing this in terms of like the number of things that can be pet versus number of things that can be small, and see which one is bigger. Right? And then he basically uses the same analysis here to show that this precondition ordering doesn't always work. One more thing, since I'm doing this, remember long back I said in the CSPs, which is also something that you're supposed to know, and I'm assuming that you know, but I don't know, many of you do not know, in constraint satisfaction problems, right? Basically, you have variables and you have to give them values, and then you can pick a variable, consider possible values, then pick another variable, consider possible values, etc. And so the question essentially would be, which variable would you pick, what value would you pick, in terms of the heuristic. Do we enough, you remember the crazy example I gave to make that heuristic? The idea of which variable would you pick and what value you would try.
Appointment.
What?
Appointment example.
Which example?
Appointment.
Okay, no. I don't know what that means, honestly. Anybody else? By the way, so there will be a big term, right? This is what I'll ask, these kinds of things. So if you have been paying attention, it should be obvious. If not, if you can't even remember jokes, then you are really asleep during the class. Yes.
Professor, you mentioned that the midterm might be next week, but misread the announcement. Do we have like an official?
No, that's a different question.
Okay.
That's a different question.
I'm just not sure.
No, but we'll get to that. But yeah, answer this
I don't
question.
remember the joke, but I know the heuristic essentially is that you pick the value that constrains the most other values.
Put the value there?
Pick the value, pick the assignment that constrains the most.
Yeah,
other
but I'm
values.
talking about two pieces. You're close, you're in the area. But you need to pick a variable and pick a value. Because in the CSP, what happens is that you have to pick a variable V1 upfront, and there's like V1 to Vn. You have to pick a variable, and in the end, everybody needs to have a value, right? Because CSP means you have to give an assignment. You will have to pick one guy to first consider. And then whichever you consider, then of the possible values you take, you have to consider a particular value. So you need a variable ordering heuristic and a value ordering heuristic. And then after that, then basically there's one more, maybe V7, and then you may go this direction, then V9, you may go this direction, etc. That's basically how CSP search works. Anybody remembers? Yes?
The branching factor versus the utility problem you mentioned.
No.
About the tree.
No.
Isn't it Bill Gates?
Yes, you win.
Appointment.
Win. Oh, there you go. That's what he meant. Okay, sorry. You had the idea all along. But then this guy is operations research guy, so he pays attention to this stuff. So if you are trying to hold a party in your home and you want to call both Bill Gates and me, and you're trying to figure out the variables are Bill Gates and me, and the values are the day in which the party is going to be held. So the first question is, who are you going to pick up the phone and call about their possible things? That would be the variable ordering. And the value ordering is having asked them, having picked up the phone to call somebody, are you going to, if there are possible values to hold the parties, including in the evening, middle of the day, at 12 o'clock, midnight, etc., which value would you first ask, are you available that time? And the whole point is you will pick the variable that is most constrained variable. Bill Gates has the least amount, the expectation is like, log is like a bozo, and so Bill Gates is not available. These days, I guess he's available all over the place, but at that time when I made this example, he had only very limited amount of availability. Right, so there are only fewer ways in which you can sell him. And pretty much any time for a party, maybe Rao would be happy to come. And so then you basically consider the size of the domain essentially to decide most constrained variable. And then the value will be the least constraining value. That is the value that puts extra constraints on the rest of the variables. And in basically the party case, you would assume that most normal people, like midnight parties are hard. You see what I'm saying? Okay, so that, by the way, that idea is connected to this idea. It's like the domain size idea, which is also connected to that idea. Right, so sometimes you want to see how many times can you make something satisfied, and the size of the domain actually winds up being that. So that's how, and I have this general sense that, especially maybe because I'm becoming old, that the way you remember things is to connect everything together. And if they're all connected together into a big mass, hopefully it won't fall through the cracks of your brain. Right? If the whole thing falls, then essentially you will be able to go and that will be completely fine. Right? But if you are not connecting, then you can forget pieces very easily. And this is the connections is how you actually remember things, essentially. Right? So it's always useful to see how things are connected. Okay. After that, then we'll get into the MDPs part. And again, this part I'm just basically going to run quickly and try to give you a sense of what's the lay of the land. The whole point is we're going to first do MDPs in the atomic level, that is atomic states. So if you did planning in atomic states, what would the problem be like? The planning, the PDL planning that we have done till now, if you did it in atomic states, what would that problem be called? What?
Is it just classical?
No, but classical planning is what we did. But the point is that, so if you did planning in atomic states, first of all, how many of you, I must have mentioned atomic states versus factored states, where states are made in terms of conditions, etc. Lots and lots of times. Atomic states, presumably you act as if they're indivisible. They're just not named states. This is S59, this is S75, etc. So the question is, if you think of planning essentially in terms of atomic states, then what is the planning problem?
Is it just satisfying conditions or doing satisfying?
It's a search problem, right?
What search problem?
Constraint search or planning search?
No. You computer science people, you have names for these things. It is a search. Of course, planning has search too. Right? But, what was planning in the end? Because ultimately one of the things is you can actually argue that I always have thought that you should understand the problem in the atomic level at least before you start thinking about what happens in the lifting level. If you don't understand it at the atomic level, then you can just delude yourself that you have some understanding in the other level. Okay? So, yeah. What?
States of problem.
What is it called?
S infinity.
No. What is it called? You're a computer science person. You can't make up names. What is it called? Yes. What? And what is it called? It's even better than A-star search, even more simpler than A-star search. What is A-star search an algorithm for?
Progression search.
No. Yes.
Graph search?
Yes, please. Please. And please understand why I'm doing this, right? Because you can delude yourself thinking that you are reinventing shiny wheels multiple times in your life. You need to understand what you're doing, right? Ultimately, deterministic planning is a graph search problem. Remember, we spent a humongous time at the progression versus regression. Nothing that I'm expecting you to know have I not talked about it with all my mind during the process. The difference, of course, is do you get it? That's a different thing. So I actually specifically pointed out that you can understand progression very easily as a graph search problem, but it's harder to understand regression as a graph search problem because regression responds to goal states, and so you are in essence starting from multiple graph vertices and trying to go towards a single initial state vertex. Remember all the discussion? Right? So you should know that deterministic planning is a graph search problem. Okay, in the bottom of it all, that's what it is. And the rest is the syntactic sugar, because basically the main reason you have the syntactic sugar essentially is if you essentially have, n Boolean state variables, then you can essentially use them to represent 2 power n atomic states. That's what you're doing. You see what I'm saying? You're trying to act as if instead of giving numbers to states, you are essentially saying what is true, what is false in each state. And if you define every state, this is what I also mentioned, it's like a feature-based representation, quote unquote. You understand what I'm saying? So if you understand the variables, if you know that you are basically going to represent the states only in terms of these Boolean state variables or Boolean features, and there are n of them, then the total number of states is 2 power n. Okay, by the way, that also makes you ask, I can also ask you the following question. On a graph, is graph search is it polynomial or NP-hard? Everybody agrees? Because nobody would have made you do the graph search in 310 if it is NP-hard problem. Right? Right? Okay? And yet, planning is a graph search, I'm saying, but I said planning is at, probably p-space complete is actually p-space, not probably, p-space complete because you can write in the PDL representation, you can write Tower of Hanoi. Tower of Hanoi essentially an exponentially long solution. So it's actually not in the class NP at all. Right? Class NP basically means that if the solution came and bit you can check that it's a solution in polynomial time. In the case of Tower of Hanoi, if somebody gives you this huge long thing, then I'll take exponential time to actually check that it is actually working right. So my question is, if graph search is polynomial time and planning is graph search, why is planning p-space complete? Or, in some cases at least NP-hard. Not you, somebody else. I'll get you in a minute. We'll see if anybody else gets it. Yes?
This is definitely the wrong answer, but is it because there's many different trajectories of like the graph search that we have to do in order to construct the plan?
No.
Yeah.
Again, yeah, no, that's not true. Anybody else? Wait, someone. Yes?
This plan space search, it's not axiom, it's not like a fixed amount of.
Okay, by the way, one more thing you have to remember. Okay, again, I'm just doing remedial computer science education just before it becomes completely useless, right? Because nobody wants computer science. They're just going to cast Claude to write their programs. They don't need to know any of this stuff. For the next 10, 5, 15 days, maybe you'll still need it. So I'm trying to desperately do remedial computer science education for you guys. You have to understand that the problem complexity and the algorithm complexity are very, very different things. A problem is NP-hard means there is no possible algorithm that you can write that solves the problem and runs in polynomial. Sorting is polynomial. But here is a great sorting algorithm. Take a permutation of the numbers, check if they are sorted. Generate test. That's only n factorial times On. Right? The fact that I can write dumb algorithms for polynomial time problems doesn't mean that the problem is hard. It means I need a better brain. Right? So the answer to that question doesn't depend on what algorithm you're using. Anybody else? Yes.
Is it that
I'm just building you up. So if you get it wrong, then we're in big trouble. Yes.
is it that some temporal problems are
No.
can be done
No. Yeah.
Compared to graph search, the sequence length can be different.
No. Yes.
Well, like your search space is exponential in respect to your like variables, right? So that's where the extra complexity is coming from.
What basically he's saying is just as there are two things. Again, remember, you're all more than seniors, right? We're going to dish you out degrees, right? And ASU is a great university. There are bozo universities in the world. And if you don't know what the heck is computational complexity, then what do you think are the rest of the bozos? And yet nobody stops, this doesn't stop anybody from like holding forth on it's like hard, it can be hard, because that's the way you impress people, right? You need to know what you're talking about, right? So there were two things that we actually came out here. One, of course, is, this is basically, how many of you have done algorithms? Yeah, you should all know these answers. Or you wasted your tuition because they are not teaching you. Even if they might have it. Okay. One basically is that complexity of a problem is independent of is different the complexity of an algorithm for the problem. In fact, in the old theory books, there used to be a nice joke. I wish I had it. So if this is a problem for which you wrote an algorithm that is taking exponential time, and your boss yells at you saying it's taking too long, why aren't you doing it right? And you could say, no, there's no easier way to do this. This is a good algorithm I came up with, there's no better way. And then they'll just say, okay, what if we hire somebody else who might write a better algorithm? And then all NP hardness basically is saying is, I couldn't find a better algorithm, and neither are all these smart people right behind me. They all tried, and none of them could find a better algorithm. And a way of theoretically stating it is that you are essentially saying you define the class NP, and the hardest problems in the class NP are NP-complete problems. And the question is, we still don't really know whether P equal to NP or not. That's one of the open millennium problems. And I'm pretty sure Claude is going to solve one of these. But the point, of course, is it's a pretty hard conjecture that P is not equal to NP. And so your boss should not be fired. That's basically the way you argue, because if you wrote for sorting a permutation-based sorting algorithm, and it's taking forever to solve anything, right? Then they can try to fire you, and they might get somebody else who might just happen to know sorting algorithms, and they'll write much better algorithm. And you are trying to tell them that nobody else can basically write a better algorithm. So that's the first part. The second part that Marco is saying essentially is complexity is a function of input size. Complexity is a function of the input size. Do you see what I'm saying? So imagine if there are S number of states in a graph. Imagine you have a planning problem. You converted that into atomic, that even though there is state variables, you can consider all possible state variable valuations, and there will be 2 power, if there are n state variables, there will be 2 power n states. So let's say S equal to 2 power n, that's the graph. And you're going to be, graph search is basically saying you won't take more than S power n time in the worst case to find a path. So it's polynomial. But then in the case of lifted scenarios, in the case of planning, when we say planning generally in automated planning, we assume without saying it so many words that we are expecting lifted representations. That means we are expecting feature-based representations or state variable-based representations. So when you do the state variable-based representations, essentially your input is log of S. Right? Right? So, and we know that the overall graph search is always S power n. So it will be e power log of S power n. That's why it is already exponential. Do you understand what I'm saying? This is something that you just have to know, because there are so many bozos in the world who don't know this. I'm not talking about Kanuts and Ars and people, smart people, but again, we are talking about a time when everybody thinks they're already an expert and nobody actually bothered to learn things. And so that's kind of important. Okay, so you have that in mind. So now the reason I brought this whole thing up is because planning in atomic level is a graph search. When you're talking about MDPs, so basically graph is the abstraction for deterministic planning. Searching paths in the graphs is the abstraction for deterministic planning. Why won't that be enough? It turns out that this is a better atomic level abstraction which is more general than the graph search. So graph search becomes part of this abstraction. It becomes a special case of this abstraction. So an MDP, just like when I give an A-star search, I'll give you a graph and say there's a start node and a goal node. Right? In MDP, there are also still states, but the interesting, actually, the canonical example to think of is something like this. Basically, you can talk in terms of states. I'll show you the notation in a minute. But this is a clean example to think about. This is the one that Intro to AI textbook talks, Russell and Marvin textbook talks about, right? So you are in the start state, and then every state has some reward, immediate reward. As soon as you get into that state, that reward washes over you, right? And you just feel it. And so, and this is like a +1 reward, is a -1 reward. And as soon as you enter those states, you'll get +1 that place and the -1 the other place. Furthermore, in small letters, we wrote that every other state has a small negative reward. Every other state is a small negative reward. Just going through that state, you will just tell you, in this example, this is a specific single example, just like you can have a specific single graph on which you can talk about how to do search in the graph, right? So we're assuming that the terminal states happens to be, those are the terminal states that are plus or minus 1. They're called terminal states because in those states you can't do any actions. If you can't do any actions, you are dead. You are sitting in that state without coming out. Remember the, what word? Ergodicity. When I'm in doubt, say ergodicity. So basically, it's the terminal states that make an MDP non-ergodic. Right? Basically, because once you go into them, you can't come out. Right? So, and then the reward is basically minus 0.4 for each other state. That sort of, think of it as basically, keep going, keep moving. It's just basically there is like a mild whip. Move. And you move like if you're a bunch of cattle, let's say, and this is like maybe the -1 is probably the butcher shop, right? And the butcher, whatever the place where they kill the cows, I don't do that. And the +1 is the happy meadows where you go in and you don't have to come back, right? So you are basically hitting these cows, the cattle, until they go to one of those states. And if they're just hanging around doing nothing, you're just giving a small whip saying, move it. That's the negative reward in this case. By the way, notice that the reward, remember this is a very specific example. I can, in a minute I'll show you, I can have rewards any which way I want for the states. Do you understand what I'm saying? I can have rewards any which way I want for the states. The reward is actually, in the graph search, you had a start state and a goal state to go to. Here there is no goal state. It's not even clear that the terminal states are, there are death states. Right? Essentially, if you go there, you die. In the sense you stop moving after that. In fact, in a minute I'll talk about it to you, but think of it as -1 is the hell and the +1 is the heaven. And one can argue that, what is going to be? Are you going to heaven? Are you going to be hell? Take it already. And you might say, I don't want either of those damn things. I want to live. And if you say that, then you have positive reward for just living. The intermediate states are negative. You see what I'm saying? If you're really depressed, you want to end it all, and I'm not saying you should do that, right? You are essentially thinking the intermediate states have huge negative reward. And so you want to end it all by either going to the heaven or hell, +1 or -1. You can change the rewards. Do you see what I'm saying for each function? And so, having said this, do you kind of realize the connection between rewards and the goals in the graph search? Reward is a generalized notion of goal. It's a generalized notion of goal. We'll talk about this multiple times, but reward function is an assembly language way of talking about goals. That is a very useful metaphor to keep in mind. Okay? And having given this, so when I'm giving the reward function, it's like saying, if I have a graph, I need to talk about, if I have a graph, I need to talk about the adjacency of nodes in the graph. From which vertex can you go to which other vertex, the child generator function. And I also need to know where am I supposed to stop, which is the goal state. In the case of MDP, those are two different parts. there is no such thing as there is a place you are supposed to stop. There are good states, there are bad states. There are some states that are terminal. Once you reach them, you can't come out. Just do the right thing. Enjoy your life. For every trajectory, imagine there is one guy who starts from start, goes to 2, then 3, then 4, and then goes to -1. Right? You can essentially say the total reward is, 1, 2, 3. So 3 times minus 0.04 plus -1. That's the total reward for that trajectory. That's the cumulative reward for that trajectory. And the idea of MDP, quote-unquote, planning is to do a policy. Whatever I said, this guy starting in here, he somehow decided when I'm in start, I'll go to this state. And when I'm in this state, I'll go to this state. When I'm in this state, I'll go to that state. That's their policy. Policy is a generalized plan. Right? And you're trying to figure out what should be your policy to optimize essentially the reward, the cumulative reward you will get. That's one way of thinking about cumulative reward you will get. If you use that policy, you're likely to get the highest cumulative reward. Assume pluses are better than minuses. That's what MDP is trying to do. Do you understand what I'm saying? That's what MDP is trying to do. Okay, now the only question, of course, is I haven't yet talked about the adjacency function. Because in graphs, you talk about which vertices are the children of which vertices. So that you can, when you expand a vertex, you know which children will come. And remember that when you think of planning as graph search, essentially the vertices, so you have S1, and if you do A1, you get to S2, you do A2, you get to, I'm sorry, if you S0, you do A1, you get to S1, you do A2, you get to S2, you do A3, you get to S3. So these are named edges, right? And the edge names are the action names, essentially. That's the connection between graph search and planning. Agreed? And so the question then would be that in this case too, I need to talk about if I'm in a state and I do some action, where will I get? That's the transition model. It's a transition model, as called the children model, child generator function for A star. Transition model in general is if I'm in this state and I do this action, what would be the state or states I will get? So we already talked about the fact that goals have been generalized to be reward functions. Right? Goals have been completely generalized to be a reward function. It's not like attainment of a set of goals at the final state. It is about the overall journey that you get to. And you actually take the reward of the overall journey. Again, as I said, not surprisingly, when in the intro to AI, when we first mentioned atomic MDP model, people are like so happy because they realize that life is more like this than graph search. Right? You're essentially trying to increase your happiness, quote unquote. And different states have different immediate happiness. Right? Yes?
Was your shirt chosen today because of the journey?
It's actually a very interesting background story, but I'll talk to you later about that. Yeah. Some of you probably will know that it's Ram Navami in India, and this happens to be it also actually, I bought this because Trust the Journey is it was my thing to say to the PhD students. And my PhD students say, it's been 5 years, how long do you think I should be there? I'll wear this t-shirt. Anyway, but the point, of course, is that it's the total journey essentially has the rewards, and you add up the cumulative rewards. It's very important to understand that, right? And it's just given as instead of giving goals, you give the reward functions in MDPs. Okay, and the other thing, of course, is the transition function. And normally, instead of just saying deterministic transition, we'll actually allow probabilistic transitions. So if you have probabilistic transitions, then you'll also support deterministic transitions. So the transition function, this is also called the model. By the way, how many of you heard of world models? That's it. Basically, variations of that are all world models. We'll talk about it a bit too. Ultimately, world model is a transition model. Okay? And PDL is a world model at a symbolic level. It's a lifted level world model. You know, graph adjacency is a world model of the graph. It is a deterministic world model. And this transition function basically is saying what is the probability that you will be in the state J if you were originally in the state I and did an action A. You see what I'm saying? And if it is 1 for one of the states and 0 for everything else, then that is a degenerate probability distribution corresponding to deterministic transitions. You understand this? Otherwise, it's stochastic transition. Yes?
Don't we treat J as a goal here?
Which one?
The J?
No, not at all. Again, please understand, by the way, please ask questions. I won't laugh today at you, but you know, if it's better to be, I mean, my general group meeting philosophy is better to be laughed at in an internal group than be laughed at externally, when people find that you don't know. This class is a big group, so you can ask any questions that you have, you know. But yes, the J is essentially, all it's saying is, if you do, you know, it's like basically, if you have a graph like this, let's say S1, S0, S1, S2, S3, S4, S5, S5. Suppose this is a graph, right? Essentially, what I am, and then basically all of these are edges have action names, right? This is A1, A2, A3, A4. This can be A5, 1, A5, 2. Each edge is an action, right? And basically this graph is saying that the probability of doing, if you are in S0 and you do action A2, if you are in S0 and you do action A2, then the probability of doing, and then the probability that you will be in S1 is equal to 1.0. And for any other thing, it is 0.0. If you do action A1, you will only get to S1, nothing else. If on the other hand, you want to talk about graphs that are basically allowing stochastic transitions, then you need to have, these graphs won't work. You need to essentially consider S0. You can do an action called A1 that will take you to S11 with 0.5 probability, S12 with 0.5 probability. And also there is another action, let's say, a 3 action called A2, which will take you to a S21, S22, S23 with, let's say, 0.33. I mean, no, actually, it can be anything, right? So 0.7, 0.2, 0.1. Is this a graph? It's not a graph. It's a hypergraph. A hypergraph, the difference between a graph and a hypergraph is in graph, each edge connects one vertex to another vertex. In a hypergraph, normally edges connect sets of vertices to sets of vertices. So what happened here is your hyper edge is A1. When you do A1, you don't get to control where you will fall. You can either go to S11 or S12 with half probability each. So in this case, in this graph, if I'm thinking of this kind of a transition, I would then say probability that if you do S0, if you're in S0 and you do A1, the probability that you will be in S11 is equal to 0.5, and similarly the probability that you will be in S12, given the same thing, is 0.5, and 0 for everybody else. This is what stochastic transitions mean. I mean, either you know it and it's obvious to you, or if you don't, then you better know it, because that's what stochastic transitions mean. And it has nothing to do with this is where you wanted to go. You are trying to go something, and in fact, one of the interesting things with So basically here the transition model for MDP is a stochastic transition model. And as I said, stochastic is more general than deterministic. So MDPs can be deterministic. So one very obvious question you have to ask while we were going through this is, what do I need to change in these definitions such that MDP actually becomes a graph? You see what I'm saying? That means there's a single goal, and essentially that goal essentially has, so that there's a particular kind of a reward function that says, actually if you have a single goal and you provide each other transition the value of the cost of that action, then you essentially will wind up having the cost of the path, which will be negative, and then the reward you get in the end. If the reward is negative, that will be also negative. Total reward, the terminal reward is negative, that's also negative. So that will be the total reward you're going to be getting in that scenario. So you can actually talk about MDPs. A special case of MDPs is essentially graph search. But we are considering the more general case. This is what MDPs are supposed to do. Okay, and interestingly, if you think in terms of environments, this here, the goals are partially satisfiable, because the reward is essentially, it's not go to a particular goal. Do the best you can. Right? And furthermore, the dynamics are stochastic, so it's not a deterministic world. Is it fully or partially observable?
Fully.
Again, these are things, please understand that these are things people who say they are in AI, and that number is increasing triple exponentially. Every day, people who are born 3 days back and say, send me an email. They find my email address and send me an email that, since my birth, I have been thinking about AI. What have you been thinking about? Right? So I'm sorry, I lost my thought. So what was the question I was asking?
Partially.
Yeah, partially or fully observable.
Partially.
Partially observable. Okay, let's do this. How many people think it is partially observable? Raise your hands. Okay, how many people think it's fully observable? Raise your hands. All the people who said partially observable, you are wrong. And you better change your understanding. Yes?
Well, there could be some latent variable that's determining that.
I'm talking about this exact problem. Don't change anything else. Right? I mean, it's like saying, is graph search stochastic or deterministic? You say stochastic. And I'll say, how can it be? Then you say, well, even though it doesn't show it when you do action A1, the world might end. That's not modeled there. The point about full versus partial observability is, does the agent know which state it currently is in? That's it. I didn't say that it doesn't. Right? So normal MDPs are actually can be called by using retronyms. Do you guys know what a retronym is, by the way? See the level of education that you get here. Yes.
Like a name is applied after.
Exactly. So they used to be ovens. And then microwave ovens came. So then you go change the name of the poor oven, which actually existed, into conventional oven. It didn't do anything wrong. It was living its life. But because you have this other thing, you go change the name of the other. So if you only had MDPs, then these are MDPs. But then there is actually a generalization of this called partially ordered MDPs, POMDPs, where the agent actually doesn't know which state it is in. It opens its eyes, it still doesn't know which state it is in. There is state uncertainty. Okay, so there is basically, just like they say that there is an app for that, there is an MDP for any problem, it turns out. Okay, so this MDP that you are talking about can also be called FOMDP, fully observable MDP. By definition, when you say MDP, you mean fully observable MDP. Okay, and that also means you can have POMDP, which is partially observable mark-ordination process. We will talk about it when we talk about partial observability, even in the deterministic case. Remember, partial observability and stochastic versus deterministic dynamics are orthogonal entities. I'm not saying I'm about to toss a coin, what do you think it will, what state would you be in? That is not the question for observability. After the toss a coin and the coin falls on the table, you still can't see the damn thing. You can't tell whether it's heads or tails. That is partial observability. You see what I'm saying? Saying that I don't yet know what will happen after the action, that's just stochasticity. Do you understand what I'm saying? Okay, so basically, those is POM DPs, and then POM DPs, and then you can talk about multi-agent POM DPs, multi-agent MDPs, MMDP. And you can also talk about DEC POM DP, which is decentralized, partially observable Markov decision process. In general, after you cross MDP, the complexity of the problem is so high that life is too short to solve them, optimally. And yet you want to understand how to solve approximately at least. But real world is essentially more like a DEC POM DP than anything else. Oh, one other thing I, by the way, forgot. One of the other interesting questions is this durative or not? Remember we talked about temporal planning in the deterministic case. Is this MDP durative or not?
No.
No. So you need a name for MDPs are not durative. You need a name for it. When will it become durative? If you have options. Remember I actually mentioned a little bit before. If you have options, then you skip over multiple states and get to like a further state. Options make MDPs, essentially MDP actions are no longer instantaneous, they're durative to some extent. And the name for that is, anybody knows?
SMDP, semi-Markov.
Exactly, SMDP. S is for semi, The point about what makes Markov decision process is this guy. This guy is like he's like the most interesting character. He and Bayes together have just cornered the entire naming market in AI. Believe it or not, at one point of time I hired a student because his last name is Markov. Right? Because imagine, I can say, as I and Markov have shown, and instantly they will believe that what I'm saying. Didn't work out, the guy left, but unfortunately. But anyway, so Markov is one of these great names in math, right? And the property of Markov property is state history independent, essentially. So what this action does in I, what this action A does in I, depends only on I, not how you got to I. You understand what I'm saying? So if you have history, which is a more general scenario, then it will be called non-Markovian. And in general, a function on space of states would be Markovian if that function is directly dependent just on the state. And it's non-Markovian if it's dependent on the history of how you got to the state. Non-Markovian is again the more general case. So this is the universe of big bad MDP world, just a few of them at least, the big names, essentially, okay? And the six in the middle is MDP, that's what we're talking about. That's like a generalization. It turns out you can also have some of these generalizations on the graphs if you start using, hypergraph terminology. But that's basically a way of thinking about these more general problems. So basically, you have stochastic worlds and generalized rewards. An action can take you to any of the set of states with some known probability as part of the model. You get rewards for visiting each state, immediate reward for visiting each state. Objective is to increase your cumulative reward. And because it is stochastic, even if you follow the quote unquote the same policy, you might do different trajectories. Do you see this? In fact, how do policies look? Policies look like that. So imagine the actions are go up, go down, go left, go right. Those are the only 4 actions in every state. Right? So normal MDP basically doesn't tell you which state, which action to do in what state. So if you want to be a drunk random walker, you go to a state, pick one of the actions that's possible, do it. And you might make it, but if you actually want to have a more kind of optimal life, then you kind of compute what is an optimal policy, quote unquote, and just follow the optimal policy. Just as in planning, you want to, like as I told you that in planning, in an ergodic world, you don't need plans. You can random walk your way on a graph until you hit the goal. Then you say, yeah, there you go. And in fact, if you want to reduce the inoptimality, you can do some post-processing and remove the loops, etc. That will be fine too. But if it's ergodic, if it's non-ergodic, while you are going through the graph, you might die. Especially if you do it real life. Now, if you do it search, it will actually be more inefficient. Okay. In this case, basically, the solution concept, there is an idea called, as I said, what is the solution concept for a problem? Remember, I said ultimately the solution concept for a classical planning problem is a sequence of actions. That's why we define the candidate set semantics from there. Right? But a solution concept for MDP is not a sequence of actions, but basically a more generalized idea called policy, which is a mapping from state to actions. If you're in this state, you do this action. You understand what I'm saying? Okay, and if it is a deterministic mapping, then it's a deterministic policy. This one is a deterministic mapping. Every time you find yourself, if you are following this policy, every time you find yourself in this state, you will always do this action. Remember that the policy being deterministic is different from the outcome being deterministic. In fact, one of the interesting things that I talked about, of course, this is, that it's a probabilistic thing, and for these kinds of problems, there's a simpler way of showing, this is the way actually, Russell and Arvid uses, which is basically to say, like if you're going in a particular direction, you will actually make the transition in that direction to the neighboring state with, let's say in this case, 0.8 probability, the bigger probability, and go on other 2 directions with 0.1 probability. Right? It's never saying you'll go backwards. Again, this is a model. You can actually say, if you have a really, really bad motor for your robot, and you say, go forward, it does something random. Right? It might go forward, it might go backward, it might go 1 step back, 1 step right, 1 step left. And in fact, and it could actually, if it's a really, really, really bad motor, then it may very well be it's 0.25 probability of going up, going down, going left, going right. That's when you better get a new robot. A really precise robot will have much higher probability in the intended, quote unquote, intended direction, some directions, for example. So if you think of that as a probability distribution, because this after all is a probability distribution over which states the probabilities of getting into those states, the lower the entropy of the, you guys say that you all done machine learning. The lower the entropy of the probability distribution, the better, the more quote unquote directed that action is. It says I will do something and more or less I will do that. The higher the entropy, the more uncertain you are. You basically, and the highest entropy for, by the way, this is something that you should know. Most of you probably know that, if you have states S1 to Sn and you're trying to define a discrete distribution, probability distribution, right? The only thing is they all should be less than point and less than 1, and they should add up to, between 0 and 1, and they should add up to 1. That's what a distribution is. So the entropy is the peakedness of the distribution, intuitively speaking. You can write it in a nicer, more formal ways. Okay, and the highest entropy comes in essence, when you assume everything is equally possible. So uniform distribution is the highest entropy. So one of the interesting questions is, if you have an action and you basically have some neighbors and you don't know which of these neighbors it will go with higher versus lower probability, and you want to really plead the fifth, saying, I have no idea, right? And the way you can see it is to say uniform distribution. Let me ask an interesting question. Uniform distribution here, right? So if you want to say, I don't know anything, the way you express your ignorance about how an action is working, we say it has uniform distribution. In fact, in general, for any distribution, if you have no idea, you guess in uniform, because that's the highest entropy distribution. This makes sense if you have a discrete universe, S1 to Sn. Imagine you have a continuous universe, that is, you have points on a line. It's a dense space. What do you do? What is the highest entropy distribution for continuous space? In fact, you can make it from minus infinity to plus infinity if it helps you. Because after all, uniform distribution doesn't make any sense, because it will be zero everywhere, because there are infinite number of possibilities. You all did machine learning, my guys. You do realize that every once in a while, when you have no idea, you take uniform distribution. And you could always say, that's because I wanted to just pick the high entropy distribution, because I didn't want to make any additional assumptions than is provided by my data or my prior experience with this action. What is the equivalent, essentially, for continuous spaces? Yes?
Isn't it just consistent in picking a random number?
No. No, we are talking about distributions. There's a name. I said uniform distribution here. So give me a name.
Gaussian.
Yes, say Gaussian, just because that's the thing that you're always using. There better be a reason why you're using it. Right? It turns out that Gaussian distribution is the highest entropy distribution for a infinite continuous space. And the way you can show that, it turns out actually, is using calculus of variations. What's calculus of variations? It's all AI, by the way. It's all become AI now. People talk about all this stuff, and people repeat this without understanding, and at some point of time, it will come and bite you if you say things that you don't understand. Right? You might do very well until about, but you might also get it. So what is calculus of variations versus calculus? You heard that name, right? How many of you heard the name calculus of variations? Really? Oh my God. Okay, I don't know what you're doing. Anyway, so calculus of variations. Calculus tries to find the minimum of a function, minimum and maximum of a function. Calculus of variation finds a minimum and maximum of a functional. That means a function form that has the best property of a certain kind. So what you are actually asking when I'm saying what is the best continuous distribution that has the highest entropy? What's the distribution with the highest entropy? Modulo some regularizing constraints. You're trying to find the type of the distribution, the actual form of the distribution. It turns out there's a lovely proof that shows that under certain reasonable assumptions, the answer is normal distribution. That's why you use normal distribution when you are in doubt. You understand what I'm saying? Anything else is essentially saying I know a little more than I'm letting you. Right? Why don't I basically, so when I said this, I know something more about the action. I know that it actually goes in the direction it's supposed to go, 0.8 after, and 0.1, 0.1 other two sides. And for example, I didn't put anything on this direction, so because that just doesn't happen. And truly speaking, in a truly ununderstood, I mean, if you want to say, I have no idea what this action does, there's no notion of neighborhood either, because first of all, the picture here is misleading, because you kind of understand the notion of neighbors because they're sharing walls, etc. For an agent, a neighbor is what their action takes them to. Do you understand what I'm saying? Right? So there was some very weird thing. I'm thinking of the following. There was a time when Ebola was making rounds in Rwanda or something. Okay, and unfortunately, that's where most of the time that particular virus fought. Right? So anyway, most people will try to run away from the places where are affected to some faraway neighboring places. One guy took a flight and got to Switzerland, and he got treated because he was rich enough that he could afford the flight action. So for him, Switzerland is actually a neighbor. Do you understand what I'm saying? Neighborhood is not geographic at all. It is what actions can you do. Right? The reason other people couldn't do is because those people don't either have a visa or they can afford the flight thing. If people have those actions, then for them it's like Switzerland is neighborhood, Mayo Clinic is neighborhood, etc., etc. So neighborhood is in terms of actions. So in fact, to say that going up action has a completely non-deterministic output, I have no idea what happens. You have to say it can go into any of the 12 states. Actually, maybe the middle one probably not. Actually, if there are any of the 12 states with equal probability, so 1/12 probability you will go to any state. Do you understand what I'm saying? The physical neighborhood has nothing whatsoever to do with the neighborhood that an agent experiences. The agent experiences the neighborhood in terms of the actions. Which is part of the reason why we talk about things like Manhattan distance versus non-Manhattan distance. In Manhattan, basically, you can only go in these ways, modulo Broadway. But really, I could argue that if you're allowed to make diagonal moves, right, I can go from here to here. So in chess, for example, weirdo neighborhood is available. Knight's neighborhood is very different from Queen's neighborhood is very different from Rook's neighborhood, etc. So the neighborhood is based on the actions that you have the ability to do. So don't confuse neighborhood in terms of physical neighborhood.
So what's a dark square?
Which one? So basically, think of it as, physically think of this as actually, so there is the abstract notion of MDP, looks like this. Let me just say, where is this? Wait a minute, actually, yeah, so abstract notion of MDP is this. This is the slide I can show if I just run a math class and I assume people understand what I'm saying, right? So that you have a finite set of states, finite action set, a Markov transition function, TSAS dash, which is the probability that if you do action A in S state S, you get to S dash. Okay, and bounded real valued Markov functions. That means the rewards are bounded. This is very, very important because the way Nick Bostrom and all the doomsayers win is basically they say there is a state with infinite negative reward, which is where apparently we all die. And if you are in such a state, then basically it becomes a degenerate MDP. You stop doing everything else because that's the most important thing to deal with. So there is no trade-off anymore if you have a state with infinite negative reward. So you have to have bounded rewards, positive or negative. Okay, so bounded reward, and then basically this can be you can generalize these things to kind of consider costs of actions, or the reward can be not just a function of state, but the function of state, the previous state, and the action you took to come. So you can talk about a C, R, S, A, S dash. That's also possible. But that doesn't change the general idea. Okay. So the point, of course, is this is the MDP definition. That's it. Now, these are states. When I showed you this, you don't think in terms of that particular kind of a maze, right? And I'm just saying that in the case of maze, basically nothing is able to get there.
So
That's basically it. So one thing is, if you read, again, how many of you have not done intro to AI? Remember what I said, how many of you have not done intro to AI? And that's where you should, slap yourself, see. Because at least if you read a good intro to AI, all of this should be just repeating. Rao is wasting our time repeating in his own way. But obviously, I'm not repeating anybody because most of you probably don't simply know this, unfortunately. But anyway, so what we are basically saying in the case of MDPs is, so here it turns out that this is a general action, but there is a special thing it's written for this domain, that if you try to go in a certain direction and you can't, then you basically stay in that same state. So if you are here and you try to go up, then with 0.8 probability you will be in this state. And 0.1 probability you try to hit this wall and stay in this, because it's the end of the wall. And 0.1 probability you try to hit this obstacle and stay here. So it actually so happens that you try to go here, with 0.8 probability you go to the next the above state, and 0.2 probability you stay in the same state. This is like basically for this specific instance, this is how we define. There is nothing MDP about it. This is just a way people tend to define this example. You can change these things, yes.
Of course, with this rule of function, you aren't, but you could penalize it for running into a wall, right? Would that be correct? Or?
No. Transitions are different from rewards. Transitions are different from rewards. Okay? A transition basically says you can't go into this state. Nothing can come into this state. And this one says nothing can go out of these two states. So these two states, you can't do any action. Whatever action you do, you just stay there. Terminal states are like that, and the obstacle states are essentially the states nothing can actually get into that state. Do you see what I'm saying? The point you're talking about, I'll get to that in a minute. That's a reward is orthogonal to transition. Don't confuse them. It's extremely important not to confuse them. Again, the levels of misunderstanding people have about this very simple concept of MDP. Because RL is essentially, you know what RL is? RL is MDP. Where you are not given the model and you are not given the reward function. Right? And so what do? Basically reward is easy to learn. If you are an actual agent, because you have pain receptors, when you go into a state, reward washes over. So basically, as you visit newer and newer states, you realize how happy you felt immediately upon entering. So you will learn the reward function just by visiting states. So RL is the learning part. It learns two things, reward function and transition function. Reward functions can be learned extremely easily because you go into that state. If you're actually, the true RL is supposed to be the agent acting in the world. And if it's acting in the world, you can't, so it's basically, you can't not feel the reward. That's the definition of reward in RL. When you go into the state, reward just washes over you. Okay? So you'll get the reward by this, every state that you happen to visit, you will, if you're a travel writer, like you go to different cities, and then some cities make you feel better, so you tell your followers, these cities are good places to go, these cities don't go. Before you didn't know. Now, of course, everything is known because enough of this travel writing is on the web, and so we have a reward function already available. Most of the city centers anyway. But in the good old exploration days, that's what used to happen. Right? The other one is transition function, which is, I don't know what actions are there. Remember how the heck you guys got here? All of us are here because Columbus was trying to go from Italy to India. I'm sorry, Spain to India. And his model of the world is screwed up. So you assume that if he goes in which direction, the first time he hits the land, that must be India. So he hit Cuba. He said, let's call it India. Let's call the people Indians. That's how you have Native Americans also called Indians, and people from India are also called Indians, because Columbus couldn't admit that was wrong. This is what I'm saying. And so that's basically what happened. So he did not have the correct transition dynamics. He just assumed that if he goes until he hits the wall, that the place he stops, that would be, India. And it just happened to be Cuba because he didn't know that there was a thing in the middle. In fact, nobody knew at that time. Okay? Anyway, so in RL you learn the reward function, you also need to learn the transition function. The way you learn the transition function is, again, you keep doing stuff. You know, the way, one simplest way of thinking about RL is if you are just a random walker. You remember random walkers? But the random walker who can feel pain and pleasure, they can learn about the world if they live long enough. You see what I'm saying? They'll go somewhere, see what it feels like, then they'll go somewhere else, they'll see what this feels like, and they'll go somewhere else, they'll put something else. They compress this into like a reward function and a transition function. That's it. And the point about transition is, when I try to take the bus from this place, you know, one time I went to city 1, but some other time I got dropped in city 2. So this bus action seems to be uncertain. Thankfully, there are no buses like that. In fact, we stabilize the world such that most of our actions at the high level are basically deterministic. But if there is stochastic dynamics, then when you do things, then suddenly you'll find yourself, for the same action from the same state might get you into a different state. So if you remember, how many times did I do action A from state S? How many of those times I went to S1, how many of the times I went to S2, how many of the times I went to S3? I take the ratios of that, that's the expected empirical probability of the transitions. This is world model. This is what RL's world model is in the most basic level. The question, of course, is, it would be great if you get to live once to check out everything and then live again to use the knowledge you gained in the first life to do the right things faster. But unfortunately, we have one life. So what you need to do is you need to both keep trying to see the new states and the rewards, and also, given the compressed version of what you have seen up until now, what is your best policy? So, with respect to your model, if you find the optimal plan, and let me show you a very nice example for this. We'll come back to this in a minute. Oh my God. Yeah, there you go. Imagine this is the thing. You didn't know these things existed. You have never been to those states. Nobody told you those states exist. Remember, this is what happened to, you might say, even if you have never been to America, how stupid are you that you went from Europe straight in the easterly direction and westerly direction and assumed that you will hit India? How did you not ever see the map? But that's nonsensical. Maps were made by other people who actually have done that. If you don't, you don't know. So imagine what happened. To understand what is happening to Columbus, you have to understand that he was working with a partial map of the world. And he is finding the optimal policy with respect to the partial map. Map is model, transition model. He didn't even know these states existed. So among the states that are available, he is doing the best he can. And the problem, unfortunately, is in certain cases, how will you ever find, imagine these are deterministic actions mostly. How many of you know how penicillin was discovered? You see where I'm going with that? Right? If things always have the same damn effect, then you will never know that certain states that you never affect, that you never reach. You will never reach them ever, because you basically know your world, you put some deterministic actions, and if these deterministic actions are always going exactly in the order they are supposed to go, you will never learn these two states exist at all. Imagine, unbeknownst to you, this was a plus 100 and this was a plus 2000 reward. If they are minus 100 and minus 2000 is better. because I didn't know, but ignorance is bliss. I avoided, that is true. But it could be plus 100 and plus 2000. You understand what I'm saying? And if you did see those states, and you only optimized your policy among the states that you know, you will have the optimal policy for incomplete model. And an optimal policy for an incomplete model can be arbitrarily far from the optimal policy for a more complete model. But then how do you get the more complete model? So if it is deterministic actions, actually it's worthwhile thinking in terms of deterministic actions. In the deterministic actions case, once you know the model, you'll actually only do the deterministic actions, so you'll never find these other actions at all. So if you have deterministic dynamics, then once in a while, you have to do the random thing. Live a little is what people say, right? I mean, don't just wake up and come to the class, however beautiful this class is. Once in a while, stop by, have a cup of coffee, talk to some random stranger, try some new drug. I couldn't say that last part. And then see if you feel good. That's how you learn about the world. Of course, you can call Gemini, which did everything because it knows all humanity has done, and it will tell you, no, you do this drug, then you will, this is what will happen to you. And so you will stop doing it. But if you don't know, and one of the other interesting things is, especially for humans, which is not for this, you don't know what your reward metric is. Most of you are basically faced with hard decisions and you don't know what do I really want. Because human reward metrics are very hard to actually decipher, even by themselves. You don't know what you like really. Because of which, by the way, there is actually an interesting thing that I tell my students, and maybe I told you here, I don't know which is, if you don't know, for example, right, whether I should date person A or person B, I can't make up my mind. Then, of course, you toss a coin. Right? You know, it comes heads, person A, tails, person B. But the interesting question is, after you toss the coin, when the coin is in the air, ask yourself, what do you wish the coin came down as? People oftentimes realize their internal preferences that way. It's a psychological thing. This has nothing to do with here. This is just a life thing. So in case you have to figure out who to date after today's class, you can ask yourself, what did you wish the coin came up as? Because that might sometimes make you realize your hidden preferences, that you didn't articulate yourself. Because our preferences may not always be consciously accessible to us. You see what I'm saying? Anyway, so the point, of course, is in these kinds of cases, when you're trying to learn the transition model with the deterministic actions, you need to, once in a while, stop doing what you're doing optimally and do some random stuff. And the random stuff that you do has no actual use on the in the current model, whatever random stuff you're doing is inoptimal execution. The only reason you're doing is, you know, for example, here you always came this side one day, hey, let me just go that side and see what happens. And then you go that side, and if it's minus 100, we would not find you. Then the rest of us say, let's not go there. This goes again, we won't go. Right? Or at least, if basically, again, I say, that which doesn't kill you makes you wiser, which is actually the point of error. So if you go into a bad state and feel a lot of pain and didn't die, then you know that that's not a good place to go to. Felt a lot of pleasure, then you know that's a good state to go to. What the heck was I doing? Unnecessarily wasting my time doing this McDonald's job when I could have been working in Burger King. Right? That's a much nicer thing, for example. So you didn't know. This part is, what is it called? Many of you know what it's called.
Is this called the curiosity approach?
No, yeah, there's a much better name for it.
Exploration.
What?
Exploration.
Exploration. Okay? So there is one of the life's greatest trade-offs in general is exploration, exploitation. Trade-off. You are exploring. Your parents wish you are exploited. Right? You're exploring because you're learning more stuff to see if you'll have a much nicer life that you will like. Your parents say, enough is enough. Start making. And so one of the interesting questions is people who don't want to do any exploration will take the very first job. So those are probably the people, who basically have just decided to drop out of elementary school. Enough studies. And then become YC Combinator startup people. Do you understand what I'm saying? So there is exploration, exploitation. Exploration has a cost, but it's a cost that you're willing to pay because, asymptotically, it can make your life much better. And of course, in a multi-agent scenario, like a humanity scenario, your exploration not only benefits you, but it benefits me too. That all the great explorers, found out parts of the world, found out penicillin. I mentioned penicillin because the way penicillin was discovered was because something, quote unquote, went wrong. Because normally anything has this sort of, stuff that develops on top, people will throw it away. That day, Alexander Fleming decided, he found that as, that basically some bacteria was dying because of that. And so then he said, hey, why not try to see what's this doing? And this is not what he was doing at all. It just happened randomly. So that's why having actions that have random effects is useful. Because here, you had to make up your mind to actually do, if it's a deterministic policy, you had to deliberately say, in this place, I will go that side. But imagine if this is it's a deterministic policy, of course, but if it's a deterministic world, then you have to actually make a conscious effort to go the other side. If it is a stochastic world, where it turns out that when you try to go forward, you go in all, backward with a slight probability, and forward in higher probability, and sideways with smaller probabilities. Eventually, you will see the other places. And the interesting question about exploration exploitation would be, in general, as you kind of can see, although I'm kind of jumping ahead and we'll come back to the MDP in a minute, so somehow after the MDP, you should be able to find the optimal policy. I'll tell you how to do it in a minute, but that's a million ways of doing it. But we'll find out one way. And the question is, if you know a partial model and a partial reward function, you assume that is the only world and try to actually do like the optimal policy for that, or approximately optimal policy for that. And you start doing it, essentially, right? And the question, of course, is if you want to throw in the exploration, then you can actually do the following thing, that you greedily follow the policy all the time. That would be considered exploitation. And a better idea might be with epsilon is a very small quantity between 0 and 1. It's a very small probability. With epsilon probability, you just do a random action from any state. And 1 minus epsilon probability, you do the action that the current optimal policy is asking you to do. That will put in exploration. The bigger the epsilon, the more the exploration, and less the exploitation. So RL and MDPs are like highly intertwined. To understand RL, you need to understand MDPs, which is why I was driving you through MDPs. So you need to understand how our policy is actually computed. If you happen to know the model and the reward, then you talk about how to learn the model and the reward, which is the RL part. That's almost a small thing. Sometimes you can combine them in the interesting ways. In fact, there are two pieces that we'll talk about when we come back. One is model free versus model based RL. What I'm describing here to you is sort of the model based RL. Because in essence, I'm kind of implicitly saying you will try to learn the transition model and the reward model and then convert them into the optimal policy. If you do that, that is model based RL. And model based RL with model is just planning. Do you understand what I'm saying? Model based RL with the model given is already planning. That's exactly what planning is. Okay, so computing the optimal policy given the model and reward is the planning activity. It's a generalized planning activity, but it's a planning activity. Getting the model is the learning activity. And basically people call both of them RL, but essentially, the planning part is better done with the planning techniques actually. And we'll talk about that later. Okay, so in the other one called model free RL one, basically the point is the model is so complicated. And since all you want to know is to compute the policy, just go directly from experience to policy. Because in the case of RL, right, in the case of MDP, model and models, the transition and reward models are given, you compute the policy. In the case of RL, the agent gets some experience, gets to convert it into reward and policy, model, reward and transition models, and then do, let's say, MDP to get the policy. Or say, screw the middle part, I'll just go from experience to the policy. If you go from experience to the policy, that's called model free RL. And the only reason that would make sense, in that case, there is no planning anymore. Right? And the only reason that makes sense, so when you don't have the model, the problem is you can't mentally simulate what happens if you do certain action. You just have to do it. Right? My classic example of that is swimming. Not because I'm bad swimmer, but it's true for everybody. In fact, I used to say that when MOOCs became very popular, and my job was once again in danger of going away, because if everybody watches one MOOC, just the 49 of you that I keep yelling at saying, why aren't you coming to my class, you won't be there. And if you're not there, I have no job. Right? Right? MOOCs means I won't have a job. So then I decided I'll be a swimming instructor. Because there is nobody who has learned swimming by watching videos, except maybe some crazy one or two people in the entire universe. You can ask Gemini, how do I swim? Model-based swimming is drowning. Why? Because swimming model is so complex that it is actually just better to try and, in essence, figure out the policy. So basically, the way you will learn what is the right thing to do in swimming is you fall into the water and then realize how to stop myself from drowning. And those actions will basically be your policy. So whenever somebody says, actually, for example, it's been said for PhD students that PhD is being dropped into the deep end of the pool and learning to swim. That's because we have no model of how to do PhD. You understand what I'm saying? It's just too complicated. If people can give random ideas about, oh, you should do this, you should keep good hours, etc. This is all like window washing. Ultimately, you can violate all of them and still be the greatest PhD student ever. You see what I'm saying? Really, PhD doing is PhD doing. You should actually be an apprentice, you hang around, you try what is working, and then you kind of figure out a model-free policy of how to do PhD. Right? So swimming is a model-free RL. There's never, basically at a higher level, maybe there is some models, but basically the actual swimming itself, you just learn the policy directly from the experience. Okay? And any normal planning things that we have been talking about here, such as travel planning, it's a model-based thing because you can get compact models. And it's much better if you have the model, you can mentally simulate. Now if you go back and if you have nothing to do, you watch the incessant number of tweets that Jan keeps writing about world models. This is all he's saying. That's it. He's just saying model-based RL is good. He hates RL, but it so happens that he also says that RL is like a cherry on the top and all that nonsense. But the basic idea is if you have a model, you don't have to do the action. You get to mental simulate. Mental simulations, nobody died because of mental simulation. They may have had a migraine, but nobody died because of mental simulation. If on the other hand, when you're trying to learn swimming, without anybody there, you get to drown once in a while. That's why lots and lots of people still drown in like Hawaii, for example. Nice looking water, suddenly, some crazy wave or some, what is that other thing called? The exploding waves are called what? The riptide, yeah. So, riptide. Basically, the problem for riptide is, unless you have experienced the riptide, you don't know what you're supposed to do. I mean, Gemini tells you, but it's very hard to actually do it at that time. Very quickly look at Gemini to see what am I supposed to do. It's very hard. So most people don't actually experience Gemini, and the people who experienced have gone. Which is my another reason I say that if RL is the only way humanity was going to survive, but if there's only a single human agent in the world, humanity would have died like it. And forget about procreation. Imagine a single human who can procreate. Right? But before procreating, they did something and died. Right? Basically they took a selfie on Grand Canyon and died. There is nobody to learn from their mistake and not do it. That's the real RL. A single agent actually working in the world in the raw, tooth and claw. And there, basically you die. Okay, so this is MDP and RL. I'll come back and talk a little bit more about the connections to MDP policy construction and also policy gradient, which is a way of constructing MDP policies. Basically, RL is just doing MDP. Right, and then the way it's going, because it's already 3:15, basically, I will probably continue this next week too for some of the other discussions about planning RL connections. I mean, I just assume that people will be very bored with whatever I'm saying, but most of you seem to be acting as if it's the first time you're hearing this stuff. I don't know what you were doing before. I mean, everybody says they are interested in RL, and they are interested in learning, they're interested in whatever else, but what are you talking about when you say talk about RL? It's more than just the, buzzwords and being able to copy paste some complex looking expressions. You have to understand what that expression is doing. Why are we doing it? And once you do that, then you can go much farther. Okay, 15 minutes. Okay, let's do the Varadacharya. Teja Sanvekar, Ritham Arya, Bhusamsha, Soham Chalwa, Vivek Reddy, Shrey Gajar, Bengal, Venkata Gumadi, Gabriel Habib, Rowan Holder, Charles Paz, George Joby, Marco Jose, Diamond Jones, Sai Saket Kambalapur, Ravikanam Ayamuri, Xuan Lu, Franz Malapo, Khushman Chanda, Ram Menon, Luka Mishevich, Sarthak Mishra, Nived Mudiam, Sania Mola, Jayesh Malpar, Nimian, Manav, Skantavatkar, Pauluri Chaya Aditya, Rishita Reddy, Tarunya Prasad, James Price, Ryan Poa, Muhammad Rahim, Arjun Rajan, Mohab Rathod, Yash Sawan, William Seru, Taha Shahi, Ashish Shekhar, Rodney Straggers, Jonathan Stenner, Ethan Tan, Manya Tiwari, Neetram, Vrinda Uday Kumar, John Woods, and Saeed Azamar. Thank you. Okay. Okay. So we basically kind of shifted from, oh, this went away. I need to connect it. So we basically shifted from talking about MDPs to talking about reinforcement learning. But the couple of things I want to point out, which is most of oral literature is grounded. So to do oral, you have to have some notion of what kind of a world you are in. You know, so basically what are the actions that, I mean, first of all, you can't do oral unless the agent has actions. And then actions should take the agent from some state to some other states, right? So the question then would become, what sorts of worlds are you in? Like depending on the world, basically all worlds are reasonable. For example, very deterministic world of the kind that we looked at in graph search, in graphs, that's also a world. You can do RL as that as the basis. And similarly, interestingly enough, you can do RL with POMDP as the basis. That means actually why not assume that the agent doesn't actually know what state they are in. You see what I'm saying? They don't know what state they are in. And so try to do RL on POMDP. In fact, if you want to do real RL, you have to do it. So the RL, the real issue is how to learn the transition model, how to learn the reward model. That's it. Depending on the kind of models you're assuming about the world, if you're assuming the world is a graph, you will learn graph transition, which is the child generator function, and graph reward, which is possibly HCAS and the final whatever HCAS and goal specifications. If you believe that you are actually in a POMDP kind of a world, then you actually need to talk about transitions when you do an action and you don't know which state you are in. You still need to be talking about what are the states you will be in. That model, okay? So it turns out that actually one of the things, this may fly over your head, but in the case when the states are partially observable, the actual effect, so the states are partially observable, then which is the best action to do, or actually what happens if you do an action at a certain, so first of all, when the states are partially observable, the agent doesn't know what state it is in. That's the whole point, right? So you can't talk about policy being state action mapping, because they don't know which state you're in. So one idea would be to kind of talk about state history to action mapping. That means talk about all the states you have gone through before you came to the state, and if you do this action, where will you be? That's one way of modeling it. An equivalent other way, it turns out, very interesting thing. So if you do it that way, then it's no longer Markovian, right? Because what you are supposed to do in this state depends not just on the state, but how you got to this state. So that would be a non-Markovian. If another way of thinking about I don't know what state I am in is I am in some distribution of states. When it's deterministic, the distribution is degenerate with 1.0 probability mass on a particular state and everything else being 0. If it is stochastic, then basically it's a normal distribution. Not normal the Gaussian distribution, it's a normal distribution. That means basically the probability mass is spread over the states. So if you think of your state not as a state, but as a set of states that you can possibly be in, right? That is actually, in the case of deterministic scenarios, that's actually what you do, and we will talk about it in like a class or two from now, when we will look at deterministic planning. In the case of deterministic planning, how do we handle partial observability? Things like conditional and conformant planning. Okay, and then what we will do in those cases basically would be to actually say that since I don't know what state I am in, I assume that I am in, so if you have states S1 to Sn, okay, suppose you have fluents are the state variables SV1 to SVM, then that is that M such things. Actually, let's make this. So there are n state variables, let's say Boolean variables, then the total number of states will be 2 power n. Right? If you have n state variables, the total number of states you can, distinct states you can talk about with those state variables will be 2 power n. Now, if you want to talk about sets of states, etc. So basically subsets of n different things. If you have a set of size n, the number of subsets of that set is 2 power n, right? But the n actually is to, so basically it would, this number of subsets would be 2 power n. This is what you are supposed to learn in Intro to AI. What you lose when you don't have eyes and hearing, etc. When you don't have sensing, then you don't know which state you are in. So you basically think that you are in some subset of states. Suddenly your state space is exponentially bigger because there are exponential number of subsets of states than there are states. And states themselves are exponential number in the number of state variables.
So
Do you see what I, yes?
the agent doesn't know what state it is in, but like from memory or something, does it have a list of actions it has?
Yes, what I'm saying is the tricky part, of course, is it all depends. I mean, we live in this world, so the usual idea is you wake up in the middle of the night in a stranger's bedroom. I won't ask why. And then you don't know exactly the layout of the room. And there are no lights. And you don't want to disturb people. And you're trying to figure out what state, exactly where in the room are you in. That's what localization is. One thing that people, for example, do is try to hit the wall and then follow the wall. Because wall will lead to the door. Because I assume that you woke up because you want to go to the bathroom or something. So you need a door. And you hit the wall and follow the wall, you get to the door. How many of you know Helen Keller? And what is the joke about Helen Keller? That Helen Keller made lots and lots of jokes about this herself. That's a nice part of it. So Helen Keller would say that when her mother got mad at her, she will put her in a cylindrical room. Right? Because following the wall doesn't give you any extra information. Right? Because in general, like knowing specific things on the walls, knowing the corners, etc., these are all the ways you state estimate. So the agent needs to figure out based on the environmental signals what state it is in. Then it needs to figure out what action does it want to do. And then it needs to figure out if it wants to do this action, what state it is likely to be in. And then do that. That's what intelligent agents do. And everything else is details. Right? And so the interesting question, of course, is in the deterministic scenarios, if there are n states, there are 2 power n subsets of states. And then if there are, if there are n state variables, then there are 2 power n states and 2 power n subsets. Now, if in the stochastic case, if you have n states, S1 to S1, S2, S3, and you want to talk about a distribution, I mentioned this in the class during the semester. If you want to talk about a distribution, which tells you your probabilistic distribution over what do you think is the probability between S1 versus S2 versus S3, that's essentially finding 3 numbers that add up to 1. 3 positive numbers that add up to 1. There are infinite number of ways of doing that. In fact, that's called a simplex. A simplex is basically a plane in which the coordinates add up to 1. A hyperplane where the coordinates add up. So in the case of POMDPs, essentially instead of thinking about the history, you can think in terms of distribution. And you can act as if what the real, there is no such thing as a state, you have a belief state. These things are called belief states. So belief state, non-deterministic belief state is actually a set of states, and stochastic belief state is a particular distribution. And if you do an action, you no longer do it in a state, you do it as a belief state. And then you get a new belief state. The whole idea of doing action in general is to reduce the uncertainty in the belief state. That's what you did when you hit the wall in your stranger's bedroom. Because at least then you know that you are near the wall. So you reduce the entropy of the distribution of your belief state. In general, when you are in partially observable worlds, actions actually are done to figure out where you are, discover yourself. That just reduces the state uncertainty. That's called the state estimation problem. After you figure out where you are, then you know what you can do from there, and then you will get a new distribution. Basically, actions are changing distributions of distributions. So if you think of MDP in the space of these distributional states, then you can model POMDP that way. And it will be more cool. Because once you know the distribution, you don't need to know all the actual states you are actually in during execution. So interestingly, while discrete MDPs can't be used directly to model POMDPs, you can use continuous MDPs where the states become belief states. And the reason I brought this up is you can actually do RL in that context. You understand belief states and the action model over the belief states, the transition model over the belief states. That's too hard. So the reason we actually look at this MDP, if you ask me, in RL, all of RL community looks at it, is, in fact, there is a, how many of you know the drunk searching for keys under the light? So the joke goes that you see this drunk who's basically searching for lights under some street light. You say, what happened, what happened? He says, I lost my keys, I'm looking for them. And you say, oh, did you lose them there? He said, no, I just lost them there somewhere, but there's no light there, so I'm searching. You understand what I'm saying? This is most of research. This is what I'm saying. You do because what can be done. You know, there's another problem that's actually harder, but it's too hard. Instead, we'll make these nice abstractions and then work on this. So the reason RL people actually look at the POMDPs is sort of the Goldilocks middle. It's better than graph search, direct graphs, and much easier than POMDP level. RL. You can generalize this. There are ways in which you can approximate this stuff there, but most of RL literature is built on top of MDPs. That's the way you essentially. I said you need to understand RL. You need to understand MDPs to understand RL. But to be completely correct, I would say you need to understand a reasonably expressive way of modeling the world, so that you can then talk about how to learn the transition model in that particular transition and reward model of that world. RL is all about learning the transition and reward model. Okay. And then, of course, so as I said, for MDP, for this Goldilocks place, basically the solution is policy. And it turns out that, in fact, for these MDPs, if there is an optimal policy, you can formally define. That's where actually I don't have the time to do all that most of the time, but you have to actually go look at those slides, those lectures, if you really want to know, and if you never heard of RL and MDPs. There is a way of talking about optimizing the expected cumulative reward a policy gets. And then you can rank all the policies in terms of the expected cumulative reward they get, where the cumulative reward for a trajectory is adding up the rewards on the trajectory. And expected reward is every time you do this policy, you might get into a different trajectory because it's a stochastic, it's a stochastic world. It's a deterministic policy, but a stochastic world. Understand the difference, right? So as you run the policy again and again, you get different trajectories. You take the average of running the policy from each of the states, and then you get basically the expected cumulative reward you get from this state if you start following this policy. And that actually is called the long-term value of the state. You understand what I'm saying? A value of a state is very different from its reward. Finding value is the point of planning. Finding reward, you don't need to do anything. You just go stand in that thing and you'll feel the reward. Did you see what I'm saying? Right? And in fact, that's another reason why reward and value are not at all correlated. They don't have to be correlated at all. You can have states that have very high positive reward and very, very negative value. Drugs. Right away you feel I'm good. But then after a while, assuming any reasonable, rational objective function, the value of the state, basically the value of the state, the long-term value of the state where you actually experience the drug high is quite low because it's all downhill from there. So reward and value are very different. And in fact, the point of planning, point of life is about dealing with the long-term value and ignoring the immediate reward, which is why you are here. After all, it will be more fun to be in an ice cream store than to be in a class, right? So this, hopefully the only reason you must be doing this is because for some weird reason you assume that the pain will somehow eventually lead to higher value state. That means the value of the state is from here, you are likely to get better jobs, hopefully. Not that there are any jobs left, that's a different story. And so you're expecting that your long-term reward will be higher, that's why you're taking this course. It's not necessarily because you like my voice, however sweet it is, yes.
I just had a quick question about definitions. For PalmDB, is it possible that the reward itself isn't even known to the agent? Or is it only
No,
the
so
agent?
the reward is felt by the agent. So the point about RL is when you are in the state. So here is an interesting thing. You knowing where you are is different from you being you are actually being in multiple places at the same time. Do you understand that, by the way? So when you wake up in the middle of the night in your friend's place, you may not know where you are. You are disoriented. But an oracle, basically from outside I can see you are exactly in one place, that particular place you are standing. And you will feel the reward of that place. Do you understand what I'm saying? There is no quantum entanglement going on here. It's not like you are in two different places like this. You are in one place, you just don't know which place you are in. It's your mind that doesn't know which place you are in. And in fact, using the reward, you may even be able to find out what state you are in. Imagine you think the uncertainty is that you are in, you may be actually in the state 1 or state 2, and it so happens from your background knowledge, state 2 has a positive reward, state 1 has a negative reward. And if you're feeling, on the whole, a positive feeling, then you must be in the positive state. So reward can actually be a signal in reducing the state uncertainty. But it's very important to again understand that the agent is in one place, but it doesn't know that it is in that place. There is no agent in the world that I know of that is simultaneously in multiple places. This is what I'm saying. There is no such thing. It is knowing your mind, mental model of where you are. That's all planning is about. That's all learning is about. From an outsider's perspective, there is like an objective truth. The question is, what do you think your state is? So, interestingly, in the PalmDB case, if you think after you do this action, you will get to a belief state of a certain distribution, and you happen to know the rewards of all those states, then you take the expected reward using that distribution. And that's what you are expecting. But once you go into the state, you will actually be in a particular state. You still don't know which one you are in. Do you understand what I'm saying? How many of you know Blitzkrieg? I believe Blitzkrieg, which is a chess with eyes closed. I mean, as if chess isn't bad enough and masochistic enough, whereas Blitzkrieg, which is it Blitzkrieg? I think it's such a one. It's an where you basically don't see the board position at all. I mean, of course, you can keep in your mind. I mean, certainly that also means that you don't see the opponent's position. And the question is, can you win? And remember, bomb with the toilet problem. Sometimes without ice, you can still reach goals. But the state space is much higher. Right? Anyway, so that's basically the PalmDB thing. But anyway, we are going to be dependent mostly on the reinforcement in the MDP model. And in the MDP model, the solution concept is a policy, and then you're trying to find which policy has the highest expected, cumulative expected reward. And the simplest ways, and of course you can also talk about things like how many policies are there, by the way. That's an interesting thing to know. Like if you have S number of states, and in each state you can do a maximum of A number of actions, then the total number of different policies is A power S. Right, because in each state you can do A number of actions, and one of A actions, and the next state one of A actions, next state one of A actions from elementary permutations. The maximum number of distinct policies, which is sort of like paths in the graph, because in plans are paths in the graph. Policies are the solution concept here. Paths are the solution concept in the graphs. So the total number of policies are A power S. And if it's PalmDB, of course, S is infinite. Right? Okay. So the interesting question is, since there are A power S policies, what do you think is and then you of course have to define, let me go, let's see. Actually I'll come back to this. Yeah. So, there's a lot actually. So value of the policy basically, as I said, is for each state, if you follow the policy from that state many times and you take the empirical expected cumulative reward, that is the value of that state with respect to that policy. And so you can then compute a value function for any policy. You can compute a value function for every state, which gives a real number to them. And you will say one policy is better, dominating another policy. If it is better, it has a better value for at least one state compared to the other policy, and at least equal or better value in every other place. And then you are trying to find the optimal policy, which is basically finding the optimal value function. And once you find the optimal value function, the policy corresponding to the value function can be computed, reverse computed. So think about, guess in terms of, like, just as to do sorting, one thing you can do is you can consider understanding sorting at the level of, I will take a permutation and check if it is sorted. That will be a sound algorithm. That's also actually a complete algorithm. Right? It's not the efficient algorithm. Right? So, and the equivalent to that in MDPs is there are only A power S policies. It's a huge number, but it's finite number. Imagine if you have no other work, if you are not minding doing n factorial permutations and checking which of them is sorted, you could also be forgiven for trying out A power S different policies and checking which of them happens to dominate everybody else. And that would be the optimal policy. Right? So I already told you how to compute the optimal policy. Its optimal policy is computed in terms of the one that gives the optimal value. Value is the long-term expected reward from the state. It's not the reward. It's the long-term expected reward from the state. In fact, as I said, the value of a state can actually be completely opposite of the current reward in terms of polarity. It could be a very low reward state, but it has a very high value. That's basically what it means. I'm kind of, all these Wall Street types, right? The first year apparently they basically are Amazon employees. First year they are made to work like working dogs, essentially. Like with no actual thing. They get tons and tons of money, but really, really hard life. And people do this because at some point of time they can become like even bigger billionaires, and then presumably then they start having life, essentially. Right? And so the reward is actually low, but the long-term value according to your model is high. That's why you do it. Okay? So that's the value of policy. And then how do you compute this policy? There are many ways. Actually, there's value iteration, policy iteration is the stuff that people talk about. So one of the things I have to understand is I already told you the equivalent of sorting by taking permutations and checking if any of them are sorted. Algorithm. It's not an efficient algorithm. But if you actually wrote that as the algorithm, what do you think is the complexity of finding optimal policy according to that algorithm? What? It's not n factorial. For the sorting, it's n factorial. It's not n factorial for everything. For the sorting, it is n factorial. It's a power s policies, and you have to evaluate each of the policies to convert them into a value function. That's actually there are ways of doing it. One simple way you can imagine is basically you roll out the policy. That means you do the action. So basically, rolling out a policy. This is a name that people keep talking about. Rolling out a policy. Rolling out a policy is, so I'm in this state. I'll do the action the state says. Then I'll figure out which state I actually got in. Then, if I actually got into this, then I do the action from there. Whatever the policy says from that action, and then keep doing this for about k steps. Normally one of the things you can do is either k steps or basically do it until you hit a terminal state. And then you have a big rollout, and then you can compute the cumulative reward that you got on that big rollout. Right? Okay. So one interesting. So if you do this, basically, if you compute the reward on that, and so you can essentially compute in basically some sort of a polynomial time, depending on you actually can get an exact algorithm, but you can also get a polynomial time algorithm, polynomial time approximate evaluation of policies. But then there are a power s policies. That means it's going to be of the order of a power s. This algorithm. You would be very, very happy to know that the efficient way to do it is what is called dynamic programming, which essentially basically computes the policy in some sort of a backwards way, which to understand it, you have to understand doing it in the finite epoch, finite horizon Markov-Radiation processes, and then generalize it to infinite horizon Markov-Radiation processes. Now you might be asking, what is this horizon? One of the questions is, how many actions are you supposed to, how many actions are you supposed to roll out before you say you have a trial? Right? In the case of finite horizon, you say you get exactly k number of rollouts. You see what I'm saying? And if you're doing k number of rollouts, then basically it's much easier. And then in the case of finite horizon, in fact, one of the interesting things is your optimal action for your state depends on how many rollouts are left. Rollout is basically the number of days you will live, number of years you will live. So if you think of what is an optimal way to do stocks, not that you have any money, or that stock market is doing well, but if you're figuring out how do I do stock versus bond mix, that's a policy. But it depends on your age. Right, you know this. Like you must have known that even if you didn't have any money, you probably heard that the old people are told that put your money under the pillow because you might need it tomorrow. For young people, you invest. Right? And so basically the idea is that optimal action depends on time to live, at the time to goal. This happens in the finite horizon Markov-Radiation process, and in the case of finite horizon Markov-Radiation process, you can essentially understand how you compute the policies correctly. Let me show you. I'll skip all this. Remember, I'm just doing like a very fast overview. I don't even know where I put this. Hopefully, I'll get it here. Yeah. Okay. So, finite horizon Markov-Radiation process is the basic thing. So, imagine you have a state S. You have two actions, A1 and A2. A1 basically has, with 0.4, it goes to S2, and 0.6, it goes to S3 states. And A1, that's A2. A1 goes 0.7, goes to S1, 0.3 goes to S4. Right? And the question is, which action should I do? Which action should I pick from state S? The question is, imagine there is a value here. That means if you have a value in, for these states with t years to live, t years to live value, t years to live, you know the values of these states, then you can find out basically the value for S in terms of the value for the same states except with t years to live. This is t plus 1 years to live. Do you understand what I'm saying? So if you know what is the optimal thing to do with t years to live, then you can convert it to the optimal thing to do in t plus 1 years to live. Basically how? It's very simple, because in this particular case, you multiply 0.7 times value of S1 plus 0.3 times value of S4, and then compare that to 0.4 times value of S2 plus 0.6 times value of S3. Whichever is bigger, that's the action you take. And whatever is coming backwards, that becomes the value of S. You understand this? This has a great name called? No, I'm so sorry. Bellman update, Bellman backup. This is Bellman backup. You see what I'm saying? The interesting thing is the point is that you have to do a max between the choices. And the max is a nonlinear operator, because of which doing Bellman update becomes costly. Okay, so if you understood this, then so basically that's what I was just saying. That's what I was saying. So Vt plus 1s is reward of being in S plus max of the expected value you will get by doing A2 and expected value you will get by doing A1. X value would be the probability times the value, t steps you do. Right? That looks like a pretty complicated operation, but it is a max, isn't it? Right? And interestingly, if in fact you happen to know the policy, imagine for a minute, you know the policy, you know exactly which action you're supposed to do in S, that would be policy evaluation instead of finding the value of the state. For the policy evaluation, you just do the action you're supposed to do. There is no more max. Imagine it turns out that you're only supposed to do action A1 in this state S according to your current policy. Then there is no max and this part won't be there. It will be a linear equation. It's a linear equation, actually you can just solve it. In fact, it's not even a linear equation, this is actually a linear update in the case of finite horizon. It's the max that throws the spanner in the works. Because of all the actions you can do, you have to pick the action that will actually give you the max backup. But you get to do this in the sequential fashion. So the basic idea is if you have a finite horizon MDP, you basically start with you have 0 time to live. If you have 0 time to live, what is the value of a state? That means you don't get to do any more actions from this state. In that case, what is the long-term value of a state? If you can't do any actions, you can't do any more actions, what is the long-term value of a state? Yeah. What? Yes. Remember, the whole thing is cumulative reward. The current state's reward plus the next state's reward plus the next state's reward plus the next state's reward. If you have no more time to live, this is it, man. That's it. Enjoy whatever you can get. So in that case, if you have 0 time to live, your immediate reward is your value. Right? So because of which you can do V0. That means with 0 time to live, you can get the values. Right? So this is basically that picture. With 0 time to live, you can get the values by just reading the rewards for the states. And then 1 time to live, you can compute the value using the Bellman update. Right? And then once you compute the 1 time to live, you can compute the 2 time to live value using the 1 time to live values. This basically is this is actually, when you heard of the word dynamic programming in algorithms courses, this was the first dynamic programming algorithm. Bellman came up with it. And this avoids a lot of unnecessary repetition of work. And it turns out this is actually polynomial time. Okay, doing this is polynomial. Then the last thing, of course, one more thing after this is, so you have to understand finite horizon MDPs to understand general MDPs. Okay, finite horizon MDPs are to some extent a weirdo. On one hand, their solution concept is harder because it's no longer what is the action given the state. It is what is the action given the state and the number of steps to do. Did you understand what I just said? So the policy is a much bigger policy. You can't just say what is the action in this state. You have to say what is the action in this state given the amount of time. So it's a bigger policy you are computing. It's basically called non-stationary policy because the policy changes based on the time to live. But computing the non-stationary policy conceptually is much simpler because this is what is happening. Then the next question becomes, what if there is no horizon? You can live infinitely long. Right? If you can live infinitely long, the problem, there are two problems. One is if you do the normal nonsensical add up all the rewards, then an infinitely long trace will have infinite rewards. And so if you have multiple traces, all of them have infinite reward, then you can't differentiate between them. So the math collapses. Do you understand what I'm saying? Because if you have infinitely long rollout, at least in theory, then each of them will have infinite total cumulative reward. Definitely. So all infinities are the same. There's no infinity plus infinity is bigger than small infinity. I mean, we are not going into the other space. Right? So there's a math problem here. So one way of handling the math problem essentially is to say that if you essentially have R1, R0 plus R1 plus R2 plus R3 plus Rk is what you are adding up, where k up to infinity, k equal to k can equal to infinity. That sequence of real numbers is guaranteed to diverge normally, unless you make it into a geometric series that converges. And one of the geometric series basically is, you start with like that 1 plus half plus 1/4 plus 1/8 plus 1/16, etc. That will converge because it has a common ratio 1 by r. So you make up a common ratio called gamma and call that discount factor, and then say if I'm getting R reward t steps from now, for me when I'm here, that's only worth gamma power tr. So immediate reward of R is equal to R. One step from now, R reward will be gamma R. 2 steps from now, R reward will be gamma square R. Do you understand what I'm saying? And so one of the interesting questions then becomes, if you do this, then it's a mathematical trick to begin with, right? This basically makes sure that the You can actually look at, for example, if you have this R1 all the way to Rk, and as long as the rewards are bounded, you can take Rmax. There is a maximum number that the reward can be, that is Rmax. So you can take Rmax out, then you essentially have something, so that the actual sum is going to be less than Rmax times this 1 plus gamma squared plus gamma power what, which is Rmax times 1 by 1 minus gamma. For finally once math is being useful, right? I mean the geometry series math that you do. That's 1 by 1 minus gamma. If you do this, then essentially math works out, and essentially there is a notion of optimal points. The question then is, having done this, half of the time, just like when we are searching for the keys under the light and then say, well, no, sometimes there is, I assume that the world is nice such that keys in the dark tend to go slightly towards the light, and that's why I'm looking at the light and it will work out. So you rationalize what you're doing. Right? And I'll give you a beautiful rationalization, which is that actually, this is the thing. If I get to, if you want $10, if I say I can give you $10 now, $10 next week, most of you will take $10 now. Pretty obvious, right? Because I want to pay. I mean, you have to have a certain level of craziness to say, I would rather take $10 next week from you than $10 now. But if on the other hand I say $10 now, or $20 next week, it's very interesting. How do you decide? How much is $20 next week worth in the current base dollars? Even more interesting, I'll give you $10 now, or $10 trillion in exactly 200 years. Looks like a pretty good deal, $10 trillion. But I won't be there, you will definitely not be there. So you basically say $10 trillion 200 years from now is worth zero to me. Unless you are one of these Elon Musk kind of characters who think that their descendants, and the guy already has like 14,000 descendants as of right now. And all of them are going to basically be very rich. I have no interest. I just want to have fun during my time. Right? And so most of us think money in the reward, future reward is discounted compared to near-term reward. Do you understand what I'm saying? So you can actually say that gamma is the factor by which you are willing to discount future reward compared to current reward. So then basically, if your gamma is 0.1, and then imagine your, like let's say if it's days, and each day is one epoch, then when I'm giving $20 1 week from now, it's really 0.1 power 7 times 20. Right? Being compared to $10. Then all of a sudden the numbers, then you might say, yeah, $10 now is much better. Now an interesting question would be, who gets to decide what the discount factor is? Hyperparameter. Right? Essentially, all you can say is the discount factor is a sort of, is basically, people just set some random discount factor. By the way, it's obvious that if you set discount factor to be 1, right? If you set the discount factor to be 1, it's basically every, $20 10 trillion years from now is better than $10 now, in that case. Okay? If you set the discount factor to be 0, then whatever I have is whatever I have. I don't care about what happens later. By the way, that second part should make you realize. In fact, you go to the following thing. It's unfortunately, I will show this. Aleppo lottery. And again, we are always in some damn war or other. That right now I'll probably say Iran instead of Aleppo, but at the time I made the slide, it was Syrian war. And there was like a major war going on in Syria. And if you go to somebody in Aleppo, and if you come here and say, hey guys, I'll get you $10 now, or $300 next week, I think most of you will take $300 next week. But imagine you are actually in Aleppo, or currently in, maybe some close to one of the power plants in Iran, unfortunately. and I say $10 now or $300 next week. There is no next week. It all depends on what the Truth Social says, whether there is next week or not. So I better take the money that you are giving me right now. Do you understand what I'm saying? So by definition, people who think the world is going to end tomorrow are going to have a gamma factor that's very close to 0. And people who think world is going to go on just the way we know, have gamma factor higher. Right? You see what I'm saying? So you can actually view gamma theoretically as related to the probability that when you are generating the trace, the probability that the epochs will end. After that, no more epochs. So, and with the gamma probability at any time, the world is going to, and 1 minus gamma probability, the world is going to, 1 minus gamma probability, the world is going to end. If gamma equal to 0, then world is going to end right after this state with 1 probability. Compared to people in Aleppo and people who dropped out of elementary school to basically make money in crypto, right? Or McDonald's, they're almost similar. What do you think can you say about gamma for graduate students, such as some of you guys and those guys? The guys who do startups versus the guys who do grad school.
We have a higher gamma.
Exactly. So the fact that there are grad students is what gives me hope that there are enough people who think that the world will be just like yesterday for quite a long time to come. You see what I'm saying? If in fact everybody believes that the world is going to end tomorrow, then this is not what you should be doing. Seriously. I love my voice, but this is not what you should be doing if you think the world is ending tomorrow. You should be prepping, quote unquote. The fact that there are like 39 of you or whatever here shows that some of you think the world will be there tomorrow. And if I'm trying to hold this class in Isfahan or something with bombs falling, you'll say, yeah, lovely. Let me see if I live tomorrow. So gamma is actually connected to the meta probability you actually assign that the world will just end, the game will end. This is different from you going into a bad state versus good state. The game ends. You understand? Like, when the game ends, there's nothing you can do anymore. So that is how you do infinite horizon Markov-Ratios processes, where you put this discount factor. The interesting question then is how to get the policy for the infinite horizon Markov-Ratios process. What you can do, it turns out, is act as if it is still a finite horizon Markov-Ratios process with large number of, remember this picture that we showed? Yeah, so here, I went 3 layers back. Imagine I have like infinite number of layers. So start still with 0 time to go. And then the next layer, there is no more time. So first layer, basically you start with the reward as the value. Then you compute the value for all the states again in terms of the previous iteration's value. It's no longer connected to time to live, it's just iteration. And these iterations can be infinite numbers. But if there is going to be an optimal policy, you would realize that between 2 iterations, value function will not change anymore. You understand what I'm saying? If it is going to be a well-behaved problem for which there is an optimal value function, despite it being an infinite horizon, MDP, it has to be the case that between 2 iterations after a while, the difference between the value functions is basically negligible. So by the way, you can realize that the value functions are vectors, right? Because value function is a value function on all the states. So it's a vector of size state space. So you are talking about the distance between 2 successive vectors. One normal way people try to use is max norm, which is take the dimension-wise difference between the value functions, absolute value, take the max of that, and say that should be less than some epsilon. And if it's less than that epsilon, then I stop going back. That's the way to do optimal value. for infinite reward. And let me take two more things and then we can go off. One of which, actually, I do love this cartoon. I should mention this to you. That I keep thinking about this Far Side cartoon. Where, these guys are walking in a desert, and then finally suddenly see, and they're like parched. And finally, suddenly see like a water fountain, and this guy is drinking the water. And the guy in the back says, no, wait, there will be another fountain with cooler water. That is optimism, my friends. Essentially, this guy has gamma equal to 1. Do you see what I'm saying? You just take the damn water because you're about to die. He says, no, we'll go farther, and so that's why that particular thing is there. The thing that I want to mention before I go away, and then we'll come back. There's a whole bunch of things I have to come back. Actually, yeah, policy gradient. One of the things that will happen as we go forward, and maybe it's kind of jumping ahead, but we're still talking about currently. I'll come back to this again next week, but actually, yes, policy gradient. Let me come back to it next week. I want to do a different thing and then let you go, which is the different kinds of MDP formulations, and then we can leave it at that. Okay, so by the way, if you don't want to do full value iteration or policy iteration, another thing you can do is this approximate thing, which is basically called look-ahead based policy construction. You can think of MDP as a game against nature. You see what I'm saying? And so what you do is you start from a state, and then you consider doing all the actions that can be done from those states. And then for each of the states, each of the actions, you know what states you can get to and with what probabilities. Right? And you can do this further and further down. Notice, those of you who know game trees, min-max algorithm, it's almost like the min-max, except in min-max you are playing against a rational opponent. In MDP you are playing against nature. And nature doesn't care that you exist. It doesn't bear any goodwill to you or doesn't bear any malice to you. It's just stochastic. You don't matter. So then you essentially take expected value. In a min-max, you take mins and maxes. Here, whenever it is nature's turn, you consider expected reward. And then you maximize the expected reward that you can get as you go level by level. And just like in min-max, you can go, the farther down you go, and then kind of initialize the value for the states farther down in some heuristic way, with the simplest heuristic being assume they just have the reward as their value, and then you back it up. That's basically very much similar to min-max 3, except it's being done online. Like for each state in front of you, it's trying to figure out what is the best action to do. This is called RTDP, real-time dynamic programming. And this is the minimum you should understand, at least. This is one way. I mean, the value and policy iteration are the optimal ways to compute things, but this is at least the approximate way to compute. And that's mostly what people do. And the last thing I want to do before you go off is, as somebody was asking, MDP, I basically talked in terms of this simple view of reward is for the states, and reward is positive. Reward, the word reward means something positive. So negative reward basically is bad, and positive reward is good. You can do the whole thing in terms of costs. In fact, one of the things is in the graph search, you don't think in terms of rewards, you think in terms of edge costs. But you can write MDPs in terms of costs too. Instead of reward, you can think in terms of costs. And it all depends on, both are equal. Essentially, if you think in terms of cost, you minimize the overall expected cost. If you think in terms of rewards, you maximize the overall expected innovative reward. In control theory, this guy, you guys know this guy, right? So when he came first, this is Dimitri Barsekas, is like a very well-known guy in control theory who actually has been doing approximate dynamic programming, basically, which is RL. And so you see the picture here, which has something written there. I still think that I should, complained to the authorities, turned him in because he was doing vandalism on that issue property. But the point being that this is the Bellman equation except in the cost form, because it's doing min. And instead of value V, they tend to write capital J cost. But the theory is exactly the same. It's like up versus down, that's it. Okay? Control theory people tend to think in terms of cost. RL folks, which came from psychology, by the way, I think which is, I showed the picture. Because originally, by the way, the word RL, reinforcement learning, came from Skinner, B.F. Skinner, who essentially said you can make animals learn things by giving them positive and negative reinforcement. And that's why that one thing that basically it's not clear who is controlling what. And basically the dog thinks that he's controlling Skinner, and Skinner thinks that he's controlling dog. But RL comes from psychology side, and psychologists think in terms of happiness. People like to increase their happiness. Control theory people think in terms of cost. People want to reduce costs. Equal, essentially. The other small difference is that instead of ascribing reward to state, you can ascribe reward to state, action, state transition. And that doesn't change anything. So you tend to wind up having both RSAS' formalisms and RS formalisms. We will just stick to RS formalisms, but they are basically syntactic. Okay, so this is basically MDP and how to get policies. And remember, we already talked about RL. RL essentially tries to get the transition function, value function, reward function, and whatever it currently has, at least the model-based one, whatever current approximation it has for model and the reward, it can use any of these algorithms to compute the optimal policy and start following it. And if you want to combine exploration with that, then follow the policy with 1 minus epsilon probability, and with epsilon probability, pick a random action and do it. This is all reinforcement learning at the atomic level. So the next two things that we have to talk about is, when to talk about connecting it to planning, we have to talk about how does reinforcement learning look and lifted level. And then we get to talk about ultimately the stuff that the paper that you read, which is what we will next. Okay, thank you. Yeah.
I sent a message on Piazza, which I didn't get a response to.
What happened?
I made a mistake when submitting homework 1, and I finally realized it this week.
Yeah, I'm sorry. Just send me send the email to me, and then I'll just send it to something. Yeah, and tell me which message number, and I'll just.
Oh, okay.
Okay.
Thank you so much. Yeah, no worries.
Okay.